We now want to take the time to look at some differential equations in action. And we're going to look at a few of the applications, and there are many, many, many applications. Take a differential equations class, but we're just going to look at a few of them. Now, one of which is very familiar. You've actually already done this, and if you're thinking this differential equation thing looks familiar, that's because you definitely did it in Calculus 1, particularly for falling bodies. So if you have acceleration, which is due to a constant, which is the way it works with gravity, on Earth, it's negative 32 feet per second squared, or negative 9.8 meters per second squared. And you have an initial velocity, v0, and an initial position, s0. Then the velocity function for a falling body is v of t equals a0t plus v0, and the position function for a falling body is s of t equals 1/2 a0t squared plus v0t plus s0. Notice that this first term is usually negative because we usually consider velocity to be negative in terms of its constant. So let's look at the Winchester 1873 lever action rifle. It was one of the most successful rifles of its day, with the Winchester company marketing it as the gun that won the West, a mythology that lived on in the movie Winchester 73, starring Jimmy Stewart, which I just happened to be watching when I was making notes, and it was released in 1950. Suppose in the movie, Jimmy Stewart fires his rifle nearly straight up into the air at the top edge of a 200-foot cliff. And notice with a 44, that should be 4440 cartridge, there was a typo in an earlier version of the notes, the muzzle velocity is 1,245 feet per second for this rifle. Okay, a couple things. If you didn't notice, they're saying he's firing from the top edge of a 200-foot cliff. So there's your S0 right there, your initial position. Your initial velocity is a two-parter because you have to know that he's firing straight up into the air. Because he's firing up, that means that your initial velocity will be positive. So this is 1245 feet per second. Because it's going up, that's why it's positive. If it was firing down the cliff, like shooting downward down the cliff, that would be negative 1245. All right, so let's find the position and velocity functions for all times at which the object is above the ground below the cliff. All right, so a of t, which is equal to a0, is a constant. It's equal to negative 32 feet per second squared, because they're obviously doing all of this in the imperial system, right? So it's got feet and seconds, not meters. No physicist would approve. All right, so then velocity, I know they gave us the formula up above, but I'll just remind us that velocity is the integral of acceleration with respect to time. So that would be the integral of negative 32 with respect to time, which would be negative 32t plus, and then our v0, right? But our v0 was given to us as 1245. So that means that v of t is equal to negative 32t plus 1245. Keep in mind that this one would be in feet per second. That would be the unit for that one. There's no period after that. All right, now s of t, the position, would be equal to the integral of v of t dt. And so that's the integral of negative 32t plus 1245 dt, which would be negative 16t squared, because we add 1 to the power and divide by 2, plus 1245t plus s0. But we were given s0. S0 is 200. So that means that s of t is equal to negative 16t squared plus 1245t plus 200. And there we have it. They asked for position and velocity. I gave them acceleration, position, and velocity. So here's velocity, and here's position. All right, next, for part B, we want to find an appropriate domain for the functions from part A. Well, it will only really work while the bullet is up in the air. So it would pay to actually look at a graph of this, which I happen to have drawn right here. So it starts off at 200. It's really small, but it's there. And it goes all the way up and all the way back down. So I'm going to draw this graph and include a scale on my paper. So it looks like this. Starts at 200, goes way up and way back down. And over here is about 0. And this up here was about 25,000. And sorry, we can kind of erase this. This was a Mythbusters episode, so if you want to check out Mythbusters episode 50, you can look into this. So right here, it starts off at 200, and then it goes way up and way back down. Now, if you're thinking 25,000, there's no way a bullet can reach that high. That's true. We'll talk about that in part E. So for part B, though, I just want to figure out an appropriate domain. So it's only going to have a valid domain while it's in the air. So I need to know where it's going to hit over here. And it hits at, and they didn't ask us for exact answers, nor did they ask us to do it by hand, so I'm not going to. It's right here. 77.973, comma 0. So I'm going to actually put that point on my graph. And I'm going to use it. All right, so 77.9730. So that means that the bullet hits the ground 77.973 seconds later. And again, no, that's not realistic. That's not the point. All right, so bullet hits ground when S of t, which is equal to negative 16t squared plus 1245t plus 200 equals 0. And that happens at, we use Desmos to solve for t. I mean, if you otherwise you have to use the quadratic formula and do it all by hand. And we find that it's about 77.973 seconds. Oop, 973. Therefore, the domain would be 0,77.973. And keep in mind, both of those would be seconds because you're talking about t. This axis right here is the t axis. This axis is actually the position. Hold on, I'm not happy with that. This is the S of t axis. Right? And this was 25,000 up here, or something like that. All right, C. For letter C, they want us to tell them, sorry, I nudged my paper there. They want us to tell them the velocity of the bullet when it hits the ground. So the velocity of bullet when it hits the ground. Okay, so that's basically saying, hey, what's V of 77.973 seconds? Because that'll be the time that it hits the ground. Okay, so that would be negative 32 times 77.973 plus 1245, and I think I already have it in Desmos. Yep, right here. Since I defined V of t and I set my A0, V0, and S0 appropriate to the question, I'm able to find it's negative 1,250.136. That would be feet per second because it's a velocity. It's negative because it's going downward. So it's positive velocity for this section of the graph. It's negative velocity for this section of the graph. And you notice it's faster than V0. That's because it had a little bit more time. So it has this extra 200 feet. So when it goes up, it leaves at 1,245. At 200 over here, it should be 1,245. And it has 200 more feet to gain speed. And so that's why it's faster. And it's negative because it's going down. All right, letter D. they want us to find find the maximum. Find the time at which the highest point of the trajectory is reached. In other words, find the max, which is up here at the tippy top of the graph, and what height it is at that time. Well, again, they didn't ask us to play, nor did they ask us to do it by hand. So I'm going to grab Desmos. I'm going to click up here on the maximum, and it's 38 I'm going to write this on my paper, and I'll show you in a second. 38.906, 24,419.141. So I can say that for part D. The maximum, I have it labeled right here, the maximum for this graph is 38.906, 24,419.141. What would that mean? So the bullet achieves maximum height at 38.906 seconds after it was fired. And reaches a max height of 24,419.141 feet. Now, there's no way that's realistic. Sorry, I don't like how smushed over that is. I'm just going to put it here underneath. That's completely unrealistic. No bullet's ever going to reach that high. That's almost the height of commercial jetliners. So maybe in some kind of weird superhero movie that would happen, but in real life that's not going to happen. And the reason is part E. Bullets only get to about 10,000 feet into the air if you fire them straight up in the air. Oh, by the way, real quick, that's tremendously fast that it's landing. That would kill a person. So that's why they don't allow celebratory gunfire, you know, where people go out and shoot guns into the air. This is why they don't allow it, because it'll land back on you and kill you. It has been known to happen. So, but bullets only go to about 10,000 feet in the air. Again, Mythbusters goes into this. So what are the things that we're missing? We're missing from this whole setup a few things. We're missing air resistance. Air resistance is the biggest one. And involved in that would be drag, right? How much drag the bullet has, which is a topic of some controversy that I'm not going to get into, how much drag bullets have. But air resistance, drag, wind is involved in that as well. Also, air density is involved in that. There's a whole bunch of other stuff going on that would really affect your results. But air resistance is key. And these are some components of what that air resistance would be made up of. We're not really doing the most realistic physics problems here.